Hello, Algebra 2. This is 10.4.1, which is solving exponential equations. So we're using some of the properties and the rules that we learned in the last two sections to solve equations with exponential functions. So by the end of this, you should be able to use those properties to do that. So an exponential equation is just an equation where the variable occurs in the exponent. So some examples of these: 6 to the 2x plus 1 equals 6 to the 3x minus 2. You could have 4 to the x equals 3, or you could have 2 to the x plus 1 equals 7, right? So those are all examples of exponential equations. So you can see you can have the variable and the exponent on both sides of the equation like we do in the first one, or you could have it in just one-sided. You can also have some complicated stuff going on in your exponents, or you could have it very simple like we do in 4 to the x. And so what we're going to use to solve a lot of these is the equality of exponents property that we talked about a few sections ago. And so what this says, just to remind you, is that if your bases are the same and you have one thing on either side of the equal sign and it's set equal to each other, then you can get rid of your bases and you can write an equation with just your exponents and set just your exponents equal to each other and solve that. It gets a little tricky when your bases aren't the same, but we'll talk about how to do that in a little bit. So the first type of equation that we want to solve are those that are simpler, that where you can rewrite it with the same base and solve it in terms of that. And so the steps to doing these are you're going to write each side of the equation so they have the same base. And so in that case, for some numbers, you're going to have to rewrite it with a new base and with different exponents. And then you'll simplify those exponents. You'll use the equality of exponents property, and you'll clear your bases and evaluate the exponents, and then you'll solve the remaining equation. So we'll go ahead and jump into some of these class examples. So for this first one, number 19, we have 5 to the x equals 25 to the 2x minus 1. So remember that 25 is the same thing as 5 squared. So what we want to do here is rewrite this 25 on the right side as 5 squared. So I'm going to rewrite my equation as 5 to the x equals 5 squared to the 2x minus 1, right? So I'm taking this 5 squared, and this 5 squared is replacing the 25, okay? So now what I can do, remember when you have an exponent inside your parentheses and then an exponent outside, you can multiply those things together. So what we can do is we can multiply this 2, that's an exponent inside the parentheses, and we can distribute that across the 2x minus 1 outside. And so what that's going to give us, we'll still have 5 to the x on the left, and then if we distribute that 2, we'll have 5 to the 4x minus 2. So now we have a situation where we have a base of 5 on either side. So what we can do is we can write an equation without those bases of 5. So my new equation is going to be x equals 4x minus 2. Now I'm going to go ahead and solve this. So I'll subtract 4x from each side, and I'll get negative 3x equals negative 2. And then I'll divide both sides by negative 3. And then x equals 2/3. And so that's our answer. And we're all done. So now we'll go ahead and we'll do number 20. So for 20, we have 2 to the negative x plus 6 equals 32 to the x. So the first thing that we want to do is see if we can rewrite it with the same base. And hopefully you remember that 32 is the same thing as 2 to the 5th. So what we'll do is we'll replace that 32 with a 2 to the 5th. So when we do that, our first line looks like 2 to the negative x plus 6 equals 2 to the 5th. Let's keep that in parentheses. And then we still have that this exponent of x on the outside. We still need to keep that. So that's why I have this x down here. So what we can do now is we can multiply this 5 and this x. And so if we do that and simplify things, we have 2 to the negative x plus 6 equals 2 to the 5x. So now we have the same base on each side, so we can clear our bases and rewrite the equation without those and with just the exponents, and we'll have negative x plus 6 equals 5x. So now I'll go ahead and I'll add x to both sides, and so 6 is 6x, and then I'll divide everything by 6, and so we get x is 1. And so that's our answer, and we're all done. So we can go on to 21. And so we're going to do the same thing here. We're going to rewrite this equation with the same bases. So we've got a 4 and a 2. And so hopefully you remember that 4 is the same thing as 2 squared. So what we can do is we can take 2 squared and put that in for 4. And so what that first line will look like is we'll have 2 squared, and we'll put that in parentheses, and we'll hold on to that exponent of x on the outside, and that's equal to 2 to the x plus 3. And so this 2 and this x, we can multiply that together. And so now we'll get 2 to the 2x equals 2 to the x plus 3. So we have the same base on each side. We can get rid of our bases, and now we have 2x equals x plus 3. And so we can solve this, subtract x, and so I have x is 3, and that's my answer, and I'm all done. So going on to, let's see, we'll skip around down to number 7. So these look kind of funny because we've got fractions equal to whole numbers, but we can rewrite that in terms of the same base. So if you think about 1/2, right, we can turn that into 4. And if you were to, well, the first issue here is 1/2 is a fraction and 4 is a whole number. But we know that if 1/2 is raised to the power of -1, we could flip that, and that would be, if we flip that fraction, it would be 2. Well, wait a second here. If we flip that, it'll be a 2 over 1 raised to the positive 1, right? You can flip the fraction and flip the sign, and then that's a 2. So then what we could do is we could say, well, if we have 1/2 and we raise that to the power of -2, so then we can flip that fraction, and that would give us 2 over 1 to the positive 2, which would be 4, right? So 4 is the same thing as 1/2 to the -2. So what we'll do is we'll take this 1/2 to the -2 and we'll put that in place of 4. So what we get is our first line, we still have our 1/2 raised to the x, and then instead of 4, we're going to have 1/2 raised to the -2. And so now what we have is we have a situation where we have our same bases, 1/2 and 1/2, so we can get rid of those. And so write an equation, and we just have x equals -2. And so that's our answer, and we're all set. So going on to number 8, we can work through this the same way. So if we recall, if we have 1/3 to the -1, well, if we were to flip that, that would be the same thing as 3 over 1 to the positive 1, which is just 3. So then if we think about, well, what power of 3 gets me to 81? And that's going to be 4. So if I have 1/3 and I raise that to the power of -4, that's the same thing as 3 over 1 raised to the positive 4, which is 81. So then we can take this 1/3 raised to the -4 and put that in place of 81. So our first line, we'll hold on to that 1/3 to the x, and then that 81, we can replace that with 1/3 raised to the -4. And so now what we can do, we've got the same base on either side of the equal sign, so we can clear those bases of 1/3, and we'll get x is -4, and there's our answer, and we're all done. So those are some examples of equations that we can solve that have the same base, or that we can rewrite with the same base. And then the other type to talk about is exponential equations that don't have the same base. And so how you're going to solve these is you're going to take the common log of each side and then rewrite it with the properties of logs, and then solve for x. So starting with number 10, if I take the common log of both sides of that, I would get log of, I would get log 2.5 raised to the x equals log 5. Now, you know that when you have an exponent on the argument of your logarithm, you can take that exponent and you can put it in front as a coefficient. So if I do that, I'm going to have x log 2.5 equals log 5. And so now we can get our variable, our x, by itself if we divide both sides by log 2.5. Right, so if I divide both sides by log of 2.5, I'm going to get x is log 5 over log 2.5. And now this is something that you can plug into your calculator. So if I do that, let's see, I'm going to do log 5, close the parentheses, divided by log of 2.5, close the parentheses. Okay, so remember to be careful with those parentheses. And I'll get x is 1.756. And that's it, and we're all done. So going on to number 11, we can do the same thing. We can take the log of both sides. So this becomes log 10x equals log 24. And so then you can take this exponent and write that in front. So you'll have x log 10 equals log 24. And so then we want to divide both sides by log 10. Right? And so if I do that, they cancel on this side. And so then I'm left with x equals log 24 divided by log 10. And so then we can punch that into our calculator. So I've got log 24, close the parentheses, divided by log 10, close your parentheses, and I'm going to get 1.380. All right, so that's the answer to number 11. Let's go on to number 12. So I'll take the log of both sides again. So I'll do log 10 to the x equals log 38. And remember, your exponents can go in front to become your coefficients. And so that'll give us x log 10 equals log 38. And if we want to get that variable by itself, we'll divide both sides by log 10. Right? And so I can cross off those log 10s. And so I'm going to get x is log 38 divided by log 10. And so I can punch this into my calculator. So I'll do log 38, close the parentheses, divided by log 10, close the parentheses, and I'm going to get x is, so my calculator says 1.579783. Well, I really only want 3 decimal places, so I've got to round. So let's say we would round that up. We're going to say 1.580. And that will be the answer here. All right, so these next two, let's see. We can do the same thing. So we'll take the log of both sides. So I'll have log 3 to the negative x is log 15, right? And I can take this negative x and throw that in the front. So I have, let's see, negative x log 3 equals log 15. And then I can divide both sides by log 3. Right? And so then those log 3's will cancel. And I'll get negative x is log 15 divided by log 3. So let's punch that into our calculator. So let's see, log 15, close your parentheses, divided by log 3, close the parentheses. And if we round that to 3 decimal places, we'll get, let's see, 2.465. And so this is a negative x. I really want a positive x. So I would just multiply both sides by negative 1. So then I would get positive x equals a negative 2.465. So that's my answer there. So that's looking good. All right, so 15, the last one, same deal. We'll take the log of both sides. So I'll have log 2 raised to the x minus 1 equals log 9. Okay, and so, well, we've got a little bit more going on with this exponent, but that's still okay. It can still become our coefficient and go in front right there. So I'll have x minus 1, and just because there's more to it than a simple x, I'll just keep that in parentheses. So I'll have x minus 1 log 2 equals log 9. So now let's divide both sides by log 2. Right, and so then I can cancel those. And so now I have x minus 1 is log 9 over log 2. And so let's see. We'll go ahead and simplify that first, and then we'll add the 1. So if I punch that log 9 over log 2 into my calculator, I'll have log 9, close the parentheses, divided by log 2, close the parentheses. So we're going to get 3.169925. So we really only want 3 decimal places. So we're going to round this to x minus 1 is 3.170, right? And we want x, not x minus 1. So we'll add 1 to both sides. So x is going to be 4.170. So that's our answer, and we're all done. So that's it for the examples in this section. So hopefully that helped you out, and you can go ahead and try the homework on your own.